Okay, so we talked in the previous video about a linear approximation, and we have that. Now we'd like to have a second degree approximation. And since we already have the linear approximation, it would make sense that we would want our quadratic to kind of make use of what we already have. So when we start out my P2 approximation, I'm going to actually include what I already have as a linear approximation. And it's okay. Then the second degree approximation, I'm going to have some coefficient, call it C2, times a quadratic, x minus a squared. So I'm just kind of following this pattern. I had an x minus a factor there. So let's have an x minus a squared. And then it's just a case of, let's figure out what this C2 is. Because once I have that, then I have a second degree approximation. So a few things that we'd like to have happen here that can help us figure out what C2 is. We would like, as happened with our P1 polynomial, right, for our function value to agree and for our derivatives to agree, as many as we can compute. So what we would like to have is that P2 of A should be the same as f of a. And we would also like P2 prime of a to agree with f prime of a. And we would also, since we can do it now, like the second derivative to agree with the function. That way, at the very least, at the point A, right, if the function's increasing at A, then our function should be increasing. If the function's decreasing, ours should be decreasing. All right, if the function's concave up at A, ours should be concave up. Right, we'd like to keep all those things lined up with our approximation. And that'll help us stay close to it, maybe just a little bit longer. Okay, so first of all, notice that if we plug in A into my P2 function, I'll have f of a, the x minus a term will cancel out, the x minus a squared term will cancel out. So we actually have the first thing checked off. P2 of a is equal to f of a. Check it off. What about P2 prime of a? Well, if we took the derivative, P2 prime of a, and then evaluated at a, well, the f of a part would be gone. Derivative of f prime of a times x minus a. Well, x minus a is a linear function, so its derivative would be 1. So we would start with f prime of a. And then the derivative for the second part would be the derivative of that x minus a quantity squared. So we multiply by that, we have 2 c2 x minus a. But if we plug a in, that would actually be a minus a, and so that term would just completely drop out. And so P2 prime of a is equal to f prime of a, and we're good. So then finally, what about the second derivative? Second derivative of P2, we want to make sure it has the same concavity. Well, if you took the derivative twice, these first two terms are gone, and that would just be the derivative of that, which would be 2c2 x minus a, and then take the derivative of that, that would just be 2c2. And we want that to be equal to f double prime of a. So that tells us then that c2, the constant for the second degree approximation, should be f triple prime of a divided by 2. F triple prime of a divided by 2. So that in the end here, we would have that the quadratic approximation, P2 of x, is actually f of a plus f prime of a times x minus a plus f double prime of a divided by 2 times x minus a quantity squared. And so this is the formula that will give us our second degree approximation. Second degree approximation. And so we're going to take a look at using this for these first and second degree polynomials to approximate our function. Okay, so we're going to turn to that in the upcoming videos. We'll see how to use this now.